Okay, so at the end of the last video, we were finishing example 3. We had found the point between charge 1 and charge 2, the 4 microcoulomb and the negative 9 microcoulomb. We found the point between them where the total potential difference was 0. And we were looking for the one on the outside on the line connecting them. And it's always on the outside of the smaller charge, the charge that's smaller in magnitude. So we have a 4 microcoulomb charge and a negative 9 microcoulomb charge. I don't want you thinking, oh, it should be on the outside of the negative 9 because negative 9 is smaller. No, ignore the negative. 4 is smaller than 9, so it'll be over here on the outside of the 4 microcoulomb. So R1 will be R1 and R2 will be 12 centimeters plus R1. So we did have V1 plus V2 equals 0, so KQ1 over R1 will equal negative KQ2 over R2. And so KQ1 over R1 will equal negative KQ2, and I think this is where the video ended, over 12 centimeters plus R1. The K's cancel, cross multiply, bring the 12 centimeters plus R1 up, and the R1 on the other side over, and now multiply through, so this will be Q1 times 12 centimeters plus Q1 times R1, and that will equal negative Q2 R1. Take the R1s to the same side, so I'd probably bring my Q2 R1 over, so Q1 R1 plus Q2 R1 will equal negative Q1 times 12 centimeters. Pull out the R1, so Q1 plus Q2, whoops, that really is a 2, equals negative Q1 times 12 centimeters. Divide both sides by the Q1 plus Q2. So negative Q1 12 centimeters divided by Q1 plus Q2. Fill in our numbers here. Q1 was the 4 microcoulombs, so negative 4 microcoulombs times 12 centimeters. I don't know where the edge of my page is. Divided by positive 4 microcoulombs plus a negative 9. So on the top we're going to have negative 48 microcoulombs centimeters, and on the bottom we're going to have negative 5 microcoulombs. 5 goes into 48, 9.6, and the negatives cancel. So 9.6 centimeters will be R1, and R2 is 12 centimeters plus that, so it will be 21.6. This one away from 2, and this one towards 1. Again, so that we know which way we're talking about, right? Away from 2 is on this side, and towards 1 will also be on this side. Okay, so that's example 3. There's one more little piece that we need to talk about before we move from electrostatics to electricity. And that's an instrument that you may have seen in 9th grade science. It's called an electroscope. And there's a few different shapes, but the one we have at school is square, and it's metal on the top and bottom and on the edges, and then it has glass, so I was going to say a cube, but it's not necessarily. Whoops, that didn't go very well. That should be over there. Okay. All right, so there we go. And then on the top there's this metal ball with a metal rod attached, and the metal rod hangs down here inside. And on the bottom of the rod are two thin tinfoil probably. We call them leaves. These are leaves. Okay? And so this is called an electroscope, and right now when the electroscope is neutral, when it's not charged, the leaves just hang straight down. But what we're going to do is we're going to take a rod, a glass rod, and we're going to rub it with fur, and it's Fluffy, my cat, that I didn't want to part with. It's a pelt, it's fake fur. But so if you rub a glass rod with fake fur, the rod becomes charged. So we're going to say the rod is negatively charged. And so when I bring it close to the metal ball of the electroscope, the leaves separate. Okay? So when this time it's not going to be three-dimensional. It's just going to... So here's the rod coming down. And so when I bring the negative rod close to the electroscope, but I don't touch, and the rod is negative, the leaves spread apart. Okay, so the question is why? The electroscope was neutral, but now when I bring the rod close, the leaves spread apart, and when I take the rod away, they go back together. So what's happening on the atomic level of the electroscope? Well, what's happening is this is metal. This is also a very bad drawing. Okay, so the rod is this ball and this shaft coming down here and the leaves are all metal. And somewhere in chemistry, you probably learned about a sea of free electrons inside a metal, right? The metals in the periodic table are the guys fated to be unhappy in life, right? The ones over on the right-hand edge, they just need 1 or 2 electrons to get a full outer shell and their life is complete. And they can steal 1 or 2 electrons for their life to be complete. So they can become happy. The ones on the very outside edge, the noble gases, their outer shell is full, so they don't have to intermingle with the other guys looking for electrons. They are nobility. They can just be by themselves. But the next 2 rows, they have to intermingle to grab electrons where they can. But they become happy. That's the right-hand side. On the left-hand side, those guys have 1 or 2 electrons too many, and they are really aggravating. They're in the outer shell all by themselves, and they're whining because they're out there alone. And so those guys, they give them away. They're like, because they like a full outer shell too, so they have 1 or 2 electrons to get rid of, but it's not really a big deal because there's the other ones who are looking for them. But the metals are stuck in the middle, and they sometimes need 4 or 5 electrons to get a full outer shell. So they're just fated to be unhappy, it seems, until they come up with the plan of, hey, you give me 5 of your electrons, and I'll give you 5 of my electrons, and then we'll be happy. And so they put their electrons together. And 2 of them do it, and they're like, I can see my 10, and right? So here they are, and they put them in between them. So this guy sees 10 electrons moving all around them. This guy sees 10 electrons moving all around them, and so they're both happy. So then another atom comes along and says, hey, I want to do that too. So he dumps his in, and what you end up getting is this sea of free electrons that move all around the nuclei of the metal. They don't stay attached to any particular nucleus. So that's what's true in a metal. So now when I bring a negatively charged rod in, this sea of free electrons in the metal here are like, oh no, there's a big nasty negative rod coming really close. Quick, everyone, run away. And so the electrons in the sea of free electrons in the electroscope all run away as far as they can, which are down into the leaves of the electroscope. And these leaves, being really thin and light, when they both become negatively charged, they separate, they repel each other. And up here on the electroscope, they leave behind this positive charged ball that's close to the rod I've brought in. But as soon as I take the rod away, these electrons are like, phew, he's gone. And then they just spread back out again, and the electroscope becomes neutral. There's been no transfer of electrons here, right? There's just a reorienting of where the electrons are inside the electroscope. But no electrons have left it. So as soon as the rod leaves, then everything goes back to normal, and the electroscope goes back to normal. Now, it's a little bit different, though, if I touch it. If I have my neutral electroscope, and now I touch with a negatively charged rod, right? Remember, when 2 objects of different charge touch, there's a transfer of charge. So now electrons from the rod go into the electroscope, and it makes